Hi everyone, I am Haya Shulman and I will show you our highlight, overcoming barriers to RPKI deployment. So, Border Gateway Protocol is the system in the internet which tells the packets which route they have to take to reach a certain destination. And to do that, each network sends announcements about its reachability in the internet, how you can reach it. And in this example that you can see, we have three networks, three autonomous systems, or for short ASs, AS10, AS2, and AS3. And AS10 says that if you have a packet which is destined to a prefix 12/16, you should send to AS10. Now, this announcement is sent to AS2. AS2 propagates this announcement further to AS3 and adds itself as the next network on the path. So what this says to AS3 is if you have a packet which is destined to an IP block 12/16, you should send first to AS2 and this will be sent to AS10. You see the path, and the path says 10.2. This means that it will propagate AS2 and AS10. And then when each network sends announcements about its reachability in the internet, after this process concludes, the traffic will traverse in the data plane exactly the path that was established in the control plane. Now, when AS3 wants to send packets to AS2, to an IP prefix 12/16, it will route the packets through AS2. The BGP is an extremely significant system in the internet because essentially every network which the packets traverse have complete access to the packets. They can see the packets, that they can modify the packets, they can drop the packets. So it is important that the packets traverse a correct route. And because of the significance of BGP, there are also many attacks against it, and most significantly prefix hijacks and redirection attacks. These attacks sometimes are benign, sometimes are intentional, meant to redirect traffic through incorrect networks, but they're always painful, even when they are benign, causing disconnection, causing financial losses, reachability problems. And there are thousands of such cases a year. Sometimes our misconfigurations are benign because someone entered incorrect parameters into the router, and sometimes these are real intended hijack attacks. Okay, so here's an example for a hijack attack. Since BGP has no security mechanisms, no built-in security mechanisms, everyone can send an announcement. Every BGP router can send an announcement claiming that they own certain prefix. And in this example, you can see a network with a network number 666, so this is AS666. It can send that to everyone, that when you want to route packets destined to 12/16, you should send to AS666. Since there is no way to verify that the announcement is really correct, an AS which believes and accepts this route will send its packet and send, instead of AS to AS2, will send to AS666. And then AS666 has access to all the traffic sent. Now, there is no security mechanisms inside BGP, but there were mechanisms which were defined. And most significant one is RPKI. It was already standardized. RPKI, or Resource Public Key Infrastructure, prevents prefix hijacks. And for this, RPKI uses two mechanisms. One is certificates, which use digital signatures to bind IP prefix to a public key. And validation, everyone validates the announcements of the networks that they really conform to the information in the certificates. How does it work? Certificates are stored in a public repository. Every network issues a certificate which says the prefix of that network is assigned to this public key. Then when networks themselves issue announcements, they sign those announcements with their secret signing key. And then every network performs validation. When a network sees a BGP announcement, it can validate that the signature on the announcement, the signature is correct, and it can validate that the information is in the announcement corresponds to the information in the certificate. Unfortunately, despite the significance of RPKI, because it could prevent traffic hijacks, whether benign or intentional, it is not widely deployed. And on both sides, it is not widely deployed. There are very few certificates, and there is almost no validation. You see, a really simple mechanism, which is digital signatures, have existed for 40 years already. Unfortunately, the deployment, even of such a simple mechanism as digital signatures, is really problematic in the internet. So what do we have? We have only 18% of the networks in the internet with certificates. This means all the other networks have not protected their IP prefix with certificate. And our work on validation showed that almost no network validates, less than 1%. So why is this? Why is this so? So almost no network will discard an invalid announcement, namely an announcement which doesn't correspond to the information that is in certificate. So this is a potential hijack. Why do networks not drop hijacks? And this is what I will show you, what are the two significant problems and how we address them in this project. Now, these studies we did in the studies of certificates and validation, we did in NDSS 18 and DSN 18 and 20. And let's look at the obstacles. So there are two significant obstacles to deployment of RPKI, and they're really central, I would say. One is invalid certificates. Why are there invalid certificates, and what does it mean, an invalid certificate? An invalid certificate means that it is a certificate which information contradicts a legitimate announcement, a legitimate BGP announcement sent by the network, which owns the IP prefix. So this announcement for anyone which performs validation will look like a hijack, while it is really not a hijack. What is the reason for this? The reason for this is that certificates are currently issued manually. And as a result, there are many errors in the certificates, errors and misconfigurations. So essentially, the human factor is the main problem towards, or one of the significant problems toward adoption of RPKI, because certificates have errors. This means they will be dropped by validating networks. And when networks drop traffic, in BGP, this means that they lose money. When you drop traffic, you lose money because in routing, you are paid for the traffic that you relay. So this creates two problems for deployment of RPKI. One, you lose money. And second, the networks which have incorrect certificates, they lose reachability. So they will not be reachable, and networks which do filtering will lose traffic. Two significant problems. You get to the situation that these networks, the early adopters or any adopters that deployed RPKI, they will have no security benefits, and they will lose money, and they will lose reachability. And the causes are too significant, as I told you, the errors, because the certificates issuance is manual. And second, when you make an error, when you configure your routing, you make an error, you don't get a feedback. So you don't even know that you made an error. This is the most significant problem here, because if I make an error, but I know that I made an error, then I can at least fix this. You don't even know that you made an error. So you think you're protected, you're not protected. It's even worse, you are disconnected from the internet. This is one of the significant obstacles towards adoption of RPKI. This is one. A second obstacle is RPKI assumes that authorities are trusted and routing is under attack. And when authorities behave correctly, security infrastructure prevents attacks. But what happens when authorities are faulty, misconfigured, compromised, or compelled to misbehave? And centralist authorities are an easy target for lawful enforcement by state sponsors and state-sponsored actors which want to impose censorship on information control or surveillance. And unfortunately, the design of RPKI creates unexpected side effects when authorities are compromised. That was not foreseen. So routing can be harmed if RPKI objects are missing, revoked, corrupted, forged. And this is exactly what state-sponsored authorities do. Now, if you probably heard of domain takedowns by the US, and if the US, this is just an example, if US has an impression that you are infringing rights, they can take your domain down and have a court order to do this. Now, there are different laws between different countries. In Europe, there are different privacy laws. In the US, there are different laws. And the fact that some country or some organization can come and disconnect you from the internet is quite significant. Now, with routing, it's difficult to do, because how can a network prevent you from routing, from having reachability? this is impossible because this requires actually attacking you, and the courts are not allowed legally to instruct or allow someone to attack you. But in contrast, RPKI introduces a point which allows you to modify its certificate, so create a new certificate, and the network will lose reachability. So without attacking the network, you have the power, RPKI gives you the power to control networks in the internet. And this means that any network is a potential victim of such attacks. If someone decides this network should be taken down, it will be taken down. Now, you may think this is a probably theoretical threat, but actually it is not. And there were many cases. I think it started, the first one was in 2012. Here I give you an example for this, where Netherlands police took RIPE NCC. This is one of the 5 regional internet registries, ordered RIPE NCC to take down a few 4 network blocks. And RIPE was taken to court. RIPE refused and was taken to court to force RIPE to do this. So you see, this is only possible with RPKI. Without RPKI, this would not have been possible. There were cases by the US also, and were other cases. So the problem is RPKI gives you the power because just if you modify an object in the repository, or if you create a new certificate, or if you remove a certificate, you can immediately cause that the network will become unreachable. And routing can be harmed via RPKI objects. Instead of giving security, you have another problem. And of course, the question nowadays, is this a correct model for the routing and for the internet, the way it works currently, that we always assume that authorities are trusted, because even if the authorities are compromised, which happens also often, the same effect could be created, because attackers could take control over the resources of some victims. So these are the 2 significant problems which we address: the problem with errors and the problem with the centralized authorities. And I'll show you our solution very quickly. Here's a solution that we did, a project that we did for fixing the problem with errors in RPKI certificates. The idea is, we identified what are the main problems in this, and the idea is to automate the generation of certificates and verification and distribution of certificates, and verification of ownership of resources in the internet. So so what we do is, the first step, we validate when someone comes and wants to issue a certificate. Currently, the process is manual. You have to communicate to someone at RIPE or with your regional internet registry, depends where you are at. And in Europe, this is RIPE NCC. You have to communicate, and then eventually they issue you a certificate. This is a problem because the network operator has to provide a lot of manual details and configure things. And the verification is also vulnerable, because what if the attacker exactly at this moment can prove that he's the owner? For instance, the attacker calls RIPE and says he's the owner of a certain prefix. And actually, this is an attack which we did, and this is not detected. So what we do is, we do automated validation of ownership. In contrast to the current ownership, in contrast to the current legal validation of ownership, which means if you're a real owner, if you have some contract to prove this, which can be easily forged, right? We do a de facto validation if you actually control the IP prefix block. And we do this verification in an automated way. So when you want to issue a certificate with our mechanism, it will be done automatically, that anyone will be able to establish that you are really the owner of this prefix. Second, as soon as we validate that you really are the owner, we issue certificates. And the issuance of certificates is also done in an automated way. We check that which prefix you own, what is your network information, and we issue a certificate. This certificate is then stored in an automated way. So essentially, there is no interaction with network operator. There is no calls, no faxes that you have to do, nothing that you need to send. It's all done in an automated way. It's cheap, as you can say, it's free, it's fast, and it's secure. That's the most significant thing. It eliminates errors and it eases adoption. Now, this is one thing. The second thing, once you registered certificates, we also show how to announce and distribute your public key in an automated way. What we do is we utilized an optional transitive attribute which is reserved for future development in BGP announcements. And this allows everyone to distribute their certificates all over the internet. Now, this project was published in a number of works in Hotnets 2018 and in NDSS 2020 and 2018. And this was received a huge attention in the IETF community. So we were invited to present it at RIPE, and it was the work on this project was reported also in popular media like Golem and others, and Telegraph. So the idea is to utilize the distributed nature of the internet, yeah, because there is no cryptography, so we need to somehow bootstrap RPKI. RPKI is not yet in place. And what we do, we use distributed agents in the internet. Each agent validates probes, sends probes to the network which wants to issue a certificate, validates really the ownership over the prefix, and identifies the parameters which are allocated to the internet. You can see this on the right hand, and the diagram. And then this is all issued. We integrated our mechanism into the validator of RIPE NCC, and we are working with the IETF on standardization and integration of our mechanism into the standard mechanism that will be used by everyone in the internet. Now, of course, there are a few questions with this mechanism. How do you distribute the key? How do you distribute the public key? What we do, we use this transitive attribute, which is allocated for future development purposes. So first, you need to see that it is supported by other systems. We saw that less than so most OASs propagate this. Registrars certify with public key, and attackers cannot register with our mechanism called DISCO instead of us. Another thing is the centralized authority. What we do is we distribute the generation of public key and signatures from one registrar to 5 registrars, essentially preventing single point of failure. And this allows us to ensure that no attacker will or government will be able to force one registrar to comply, because you have to go to all 5 of them, and this is much more difficult. And this was also received a lot of attention. This was published at the IETF workshop and presented already and reported by APNIC and by different RIRs. We also published it at Azorix. And just to conclude, because I'm over time, if you want more information, of course, I'm happy to provide you more information in the papers. But essentially, in this work and this highlight, we solved 2 critical problems in the RPKI, allowing securing the internet routing infrastructure. And this is not just a theoretical work which produced papers, but we are actually have both our mechanism being adopted by the IETF and probably will be used hopefully soon in the internet.